Hello, my name is Christine, and my poster is about wildfire PM 2.5 forecasting accuracy and its impacts on decision making with a focus on Los Angeles wildfires on January 10th, 2025. If you haven't heard already, the LA wildfires occurred earlier this year from January 7th to the 31st, exacerbated by drought, low humidity, vegetation buildup, and the Santa Ana winds. Wildfires are a major source of PM 2.5, a harmful air pollutant. However, forecasting PM 2.5 concentrations is challenging due to uncertainties in fire emissions, plume rise, and model inputs. This study aims to evaluate forecast accuracy of several models and its implications for policy and decision making. For the study site, the boundaries extend beyond LA due to wind transport. To analyze model accuracy, we use EPA Air Now data from 41 stations to compare with model predictions and US 2020 census data to estimate affected populations. The models analyzed include HER, ECCC, NAQFC, NAPS, GOCF, and GEFS, as well as their ensemble mean and median. Figure 3 maps out boundaries for HER, ECCC, and NAQFC, since they are regional models, while NAPS, GOCF, and GEFS are global models. Figure 4 shows model predictions for January 10th during the fire and January 14th after the fire. The left figure shows high variability in PM 2.5 predictions, while the right figure is more uniform. This highlights high uncertainty in wildfire PM 2.5 predictions compared to post-fire conditions. Figure 5D categorizes populations exposed to different PM 2.5 levels, while Figure 5A maps their distribution. Figure 5B shows high standard deviation in PM 2.5 levels between models, reinforcing the uncertainty of predictions during wildfires. This is problematic as sensitive groups rely on accurate forecasts for timely warnings. Figure 6 further illustrates how exposure estimates vary by model. Notably, NAPS, ECCC, and HER underestimate exposure on January 10th, underscoring forecasting challenges. In Table 1, we assess correlation, mean bias error, hit ratio, and false alarm ratio. One model that stands out is GEFS, with an extremely high mean bias error indicating overestimation, as well as the lowest hit ratio and the highest false alarm ratio indicating poor accuracy. The combination of multiple models is typically done to improve outputs. However, in this case, ensemble mean results were very poor, likely due to the GEFS model. Because of that, we analyzed the ensemble median and found it more robust to extremes, resulting in better results overall compared to the mean. Figure 7 compares PM 2.5 forecasts at 3 locations. GEFS and NAQFC overestimate PM 2.5 on January 10th for all locations, while GOCF performs best at location 1 and ECCC and NAPS at location 2 and 3. Shows high accuracy for location 3, highlighting how model accuracy varies by region. To conclude, we found that the ensemble mean is unreliable due to overestimation, while the ensemble median performs better. Further improvements could include weighted ensemble methods like regression techniques. And finally, when it comes to decision and policy making, forecast accuracy is crucial for public health warnings, regulatory policies and emission controls, emergency response and mitigation strategies, long-term planning, and climate and energy policies. Underestimation may jeopardize health and weaken regulations, while overestimation could cause unnecessary restrictions, panic, and wasted resources. To end this, I wanted to thank NASA, Earth Action Wildland Fires for funding, as well as NASA, NOAA, ECCC, and the EPA for PM 2.5 emission data. Thank you very much.